Continuing on with learning target 1D in this video, and we will be doing more examples for the intermediate value theorem. So in the first part of this video, we learned about what the intermediate value theorem is, and we looked at one example. So as a refresher, the intermediate value theorem says that if f of x is continuous, so I have to require that our function is continuous on the closed interval from a to b, then for every value m in between f of a and f of b, so if I go down here to the picture, which is really helpful as we're thinking through this, m is a y value. So for every y value in between f of a and f of b, there exists at least one value c in between a and b such that f of c has to be equal to m. So here c is our x value, and then m is representing f of c, which is the y value we would get by substituting in c into our continuous function f of x. Overall, what the intermediate value theorem tells us is that if I have a continuous function, I cannot skip over any values. So to simplify the intermediate value theorem down as much as we can, if a function is continuous, we cannot skip over any values because that function has to, if we're thinking about drawing it on the page, we have to be continuous, so our pencil is not going to be picked up. There are no values that are skipped, so every single y value exists. One other thing to keep in mind is that this is an existence theorem, and what that means is the intermediate value theorem tells us that the value exists, but it cannot tell us what the specific value is. So using the intermediate value theorem, I can only prove that the value exists. I cannot prove that the value is specifically equal to a certain y value. Let's scroll down and check on a few examples. So as you guys saw in the example in the first video, there's a lot of writing and justification that goes into these types of problems, and that's going to be the case for any problem that requires us to use a theorem to justify our answer. So before we jump into examples, let's think about how we can format our justification. There are three things that has to be true. The first is that we have to explain and identify that the conditions of the theorem are met. And what that corresponds to for the intermediate value theorem is that we need to state, or we need to prove, that our function is continuous. The intermediate value theorem will not work unless that function is continuous, and therefore that has to be the first part of our explanation if we're going to justify using the intermediate value theorem. The second thing is that we need to state and calculate any relevant mathematical data. So for the intermediate value theorem, the data that we're looking at is the y values f of a and f of b. And we want to be able to prove that those two values are around the given value that we're looking for. So that second piece of information, we have to state that inequality that is being computed from those y values. Then the third part is just concluding our statement using the theorem's name. So the last part, if we're thinking about it in terms of the intermediate value theorem, is that by the intermediate value theorem, and you are allowed to shorthand that using IVT on any learning check or assessment in class or on the AP test, it is fair game to use the shorthand of IVT instead of writing out intermediate value theorem. Then there exists that value c that we were looking for in whatever interval the problem's asking about, such that f of c equals that m value. Let me change to a pen here, which was that value that we're sandwiching the y values in between. So these are those m values that the question was asking us about. And we're going to kind of use this template to help us formate our thought process. So to refresh it again, the first thing that we have to have is we have to identify and explain that the conditions of the theorem are met. Without this first step, the rest of our work is not justified and actually is not true, because I have to have that the function is continuous to be able to use the intermediate value theorem. The second is we need to state any relevant mathematical data, and we might possibly need to compute something like you guys did in that first example in the last video. So sometimes we need to compute something, sometimes it is directly given, or there's a lot of information given and we have to extract that certain data that we're looking at. And then the last thing is we have to conclude our statement using the theorem's name to know which theorem we're justifying about. One word of caution is that throughout this course, we are going to see quite a few theorems. And not only will we have to apply the theorems, but we'll also have to identify which theorems to use for the situation that is given. The intermediate value theorem is used when the given information about a function f of x and is asking about that same function f of x. So throughout this course, we are going to see a couple theorems. And in all of these problems, we are applying the intermediate value theorem since that's the only concept we're talking about. But once we start building and putting a lot of these concepts together, the problems are not going to specifically state which theorem that they want you to use. Instead, we have to interpret based off of what the question is asking and what the question is giving us, which theorem would be most appropriate. So as this might not make much sense now, but as we see throughout this course and we see a couple theorems, the intermediate value theorem is used when we are given information about a function f of x and asked about that same function f of x. That is very key. So the intermediate value theorem is all about if I'm given information about one function f of x and I'm asked about that same function f of x. Let's look at our first example in this video. So it says use the intermediate value theorem to show that f of x, which equals 2x cubed minus x plus 3, takes on the value 3.25 for some value x in between -1 to 1. I want to go straight to a picture so that we can really visualize what's happening. So our interval this time is running between -1 and 1 on the x-axis, and then we have this function f of x, which is a cubic, so we do have a polynomial, and that will be helpful because we have to be able to prove that this function is continuous, and polynomials are continuous. Looks really messy, but that was a y. So we do have a polynomial here, and it's asking us to show that there has to be some value x in between -1 to 1 such that that value, the corresponding y value, will be 3.25. Now they're not asking us to find the specific x value. We would have to honestly do a lot of trial and error to figure out what the specific x value is, but they just want us to prove that that x value exists instead. So on a graph, when we're looking at this, let's get quite a few tick marks up here. We're trying to show that there exists a value at 3.25. So 3.25 is roughly here. So we're kind of wanting to make sure that we cross over this dotted line. And if I have to cross over this dotted line at some point, then that means that there exists an x value such that the y value is equal to 3.25. Couple ways this could happen. I could start with a value that's bigger than 3.25, and then I could go down to a smaller value than 3.25. That would force me to have to cross over this 3.25 line. Or we could start with a y value that is lower than 3.25 and then increase and move up above and cross over. The other option is that we can cross over quite a few times. So the intermediate value theorem shows or proves to us that it exists at least once. That doesn't mean it exists only once. I could have a graph that crosses over many times. Maybe it starts above 3.25, goes down below, then goes back up again, and then goes down below again. And in that case, I would cross over 3 times. So it is just an existence theorem. We're not finding the specific values. We're just proving that there exists at least one point where that will happen. Okay, let's format out our thought process here, and I want to make sure we can have all 3 of those statements up. So the first thing that I want to do is I want to explain and identify that the conditions are met. So for the intermediate value theorem, I need my function to be continuous. And in this case, they don't tell me that f of x is continuous, but I can interpret that f of x is a cubic polynomial, and therefore polynomials are continuous. So let's write that down. So since f of x is a polynomial, then f of x is continuous. Oops. I almost started using a shorthand right away, but I want to make sure I'm writing this all out. So since f of x is a polynomial, then f of x is continuous on technically all real numbers, and I'm going to shorthand all real numbers with ARN. since the domain of polynomials are all real numbers. But we're only specifically interested in -1 to 1, so all real numbers includes -1 to 1. The next thing we have to figure out is state or calculate some relevant mathematical data. So for the intermediate value theorem, what that means is I need to compute a value that's bigger than 3.25 and one that's smaller than. And that means that I have to cross over since the function is continuous. Well, they gave me this interval of -1 to 1, so I'm going to start by using those values and see what that gives me. So I'm going to start by computing f of -1. Why don't you guys pause the video right now and compute both f of -1 and f of 1 on your own first, and then we'll check them together. So to compute f of -1, I'm going to sub -1 in for all the x's. So I'll get 2 times -1 cubed minus a -1, plus 3. There we go. So -1 cubed will give me a -1. 2 times that -1 will give me a -2. I have a double negative there, so I end up with +1 and then +3. Simplifying that down, I get a value of 2. So on the graph, what that means is that at -1, I have this y value of 2. So I have that point right there in blue on the graph by plugging -1 into that function. We can do the same thing for +1. If I substitute in +1, I'm looking at 2 times +1 cubed minus 1 plus 3. Simplifying this down, we get 2 minus 1 plus 3, so I end up with +4 then. So if I were to plot that at x equals 1, I'm up here at +1, 2, 3, 4. What that tells me then is since I have a value that is smaller than 3.25 and I move to a value that is bigger than 3.25, I have to cross through it at least once since this graph is continuous. So one option could be is maybe it curves a little bit and it crosses through like that, and I hit 3.25 right there. I don't know exactly where I hit 3.25. It doesn't matter where I hit 3.25. This question is just asking that that value exists at least. We could also have maybe that it crosses through more than once. So just because I know that I go from smaller to bigger doesn't mean I have to stay like that. I could have this graph that comes up and down and then maybe curves again. And I, in that case, cross through 3.25 here 1, 2, 3 times. It doesn't matter what scenario we are in. All that it matters is that because f of -1 was equal to 2, which is less than 3.25, and that f of 1, which is equal to 4, is greater than 3.25, and because this function is continuous, then we have to cross through 3.25. So let's finish our kind of statement here. This is my work that I need to show so that I know those values and I know that those values exist, but for me to state my mathematical data, that's where I'm looking at this inequality. So the inequality we're looking at here is our m value for this example is 3.25. So I want to start with the value that is smaller than, which would be f of -1. So as I continue on our statement, I have since f of -1, which is equal to 2, if you would like to write that down for your memory, that is less than that 3.25 value that we were looking at, which is less than 4, which is equal to that f of 1 value. Now, one thing I want to point out is that it is not necessary to write the 2 and the 4, but it is necessary to have the f of -1 and the f of +1. And the reason being is I want to be emphasizing the fact that this 3.25 is a y value, and so if I'm sandwiching it in between 2 and 4, yes, that's true, but that's not emphasizing that those values are coming from our f of -1 and our f of 1. So it's important to include that function notation there to show that we have a y value. Finishing off our conclusion, because that would be our third part there, is write a conclusion using the theorem's name. Is I'm going to say by the intermediate value theorem, so by IVT, if I shorthand that, there exists, since that's what I'm trying to prove, a value, let's call it C, since I really don't know what that value is, in between -1 to 1, since that was the interval that we were working on the x-axis, such that, oops, that was an H, such that f of c has to be equal to 3.25. That magical y value that we were trying to show does exist. So as I can see here, I did put this kind of work brackets around it. This is still necessary for me to show because otherwise I wouldn't have known which way the inequalities would be facing, or if -1 and 1 would even help produce those inequalities. So I have my three pieces here that we can see. The first part is I'm stating that the conditions are met in the theorem. So since f of x is a polynomial, then f of x is continuous. I have my inequality. I first computed my work and then I stated that in my inequality. So since f of -1 is less than that 3.25 is less than f of 1, then my third part is my conclusion to it. So by the intermediate value theorem, then there exists a value c in -1 to 1 such that f of c has to be equal to 3.25. And again, just make sure we're emphasizing this 3.25 is dealing with y values by using the f of -1 and f of 1 notation. And when in doubt, I think it's always helpful to have a picture to really visualize what's happening here, and we can see kind of how that scenario plays out. Although we don't know exactly what happens between our two blue points here. So the green line I did draw in a different color because that's not necessarily what this graph looks like. But I do know that I have these two blue points here on our graph at -1, 2 and 1, 4. And because the function is continuous, at some point I have to cross over that 3.25 boundary line there. But it could happen more than once as well, and I want us to keep that in mind. Let's look at a different type of style of the question. So in the first example in the last video and in this example that we saw, you guys were given a function and then we were asked to compute values and show that we can cross over that magical number. Well, there's another way to ask these questions. The AP test really likes to ask these from a table format because it really forces you to think about what does the intermediate value theorem mean and how can I interpret and apply that from data points versus a function that's given to me. So let's read through this first example. It says the temperature f of t in Palm Springs was recorded every 30 minutes for a 3-hour period beginning at 7 a.m. as shown in the table below. Note that the temperature is continuous. So they're telling us that the function f of t is continuous, although they never define for us what f of t is equal to, and I cannot figure that out. I do know that that function is continuous. The question they're asking us is there a time t between 7 a.m. and 10 a.m. when the temperature in Palm Springs was 80 degrees exactly? They want us to explain our answer. So a couple things I noticed right away. They're giving me a function f of t that's representing temperature, and they're telling me that that function is continuous. Now I don't know what f of t is equal to. I can't write out a function for it. I just have 1, 2, 3, 4, 5, 6, 7 data points about f of t that they gave us. The other thing I notice is this phrase is there. So it doesn't say find the time. It says is there a time. This is an existence type of question. So they're saying does that time exist in between, in this case, 7 a.m. and 10 a.m., where the temperature was exactly 80 degrees. Let's look at the table and the data we have. So in our top column here, this is our time values. This would be equivalent to our x values. So they're saying at 7 a.m. that must be recording to time 0, and then every 30 minutes from there we can see the time change. So time 0 is our 7 a.m., then it looks like we have 7:30, 8, 8:30, 9, 9:30, and then we're back here at 10 a.m. So this information does line up with the problem, and that's important to think about. They're moving in increments of 30 because every 30 minutes the temperature was checked. And then f of t is our temperature. These are our y values that we're getting. So at 7 a.m. or at time 0, we were at 64 degrees. At time 30 or 7:30 a.m., we were at temperature 70 degrees. Then all the way up to at 10 a.m., we made it all the way up to 90 degrees, which isn't too surprising for Palm Springs, especially as we're getting towards the summertime. So let's think about this. Do you guys think that there exists a time where the temperature is exactly 80 degrees? Why don't you guys look at that data in the table and think about, would that even be possible for this temperature to hit 80 degrees? So yes, it's definitely going to happen. And the reason I know that is because of the intermediate value theorem. So as I'm thinking about the three things, one, two, three, the three things that I need my conditions to be met. So I need my function to be continuous. There we go. And they told me my function's continuous. I need to somehow have an interval around that magic number. So in this case, that magic number we're looking for is 80. And if I look at this, between 64 to 90 degrees, at some point I have to cross through 80. So I definitely have that interval. We're going from 64 to 90, and we're going to narrow that down even more, but I have to somehow magically pass through 80 if my function is continuous, and then we will write our conclusion together. So let's start with the first part of stating that our function is continuous. Well, they gave it to us, but I still need to write that down. So I'm going to start with the fact that since f of t is continuous, they gave that to me. I don't have to prove that f of t is continuous, but I do need to state that that is part of the problem that is given. So since f of t is continuous, the second part that I need to deal with this inequality statement here. Well, I could go from 64 to 90 and say that 80 degrees is in between those two numbers, but I want to narrow this down as much as I possibly can. Where's the smallest interval that I can narrow it down between? What two time values does that happen in between? So the smallest I can narrow it down to is between the 78 and 83 degrees, which is happening when we're in between 90 and 120 in terms of the time. So for me to state that, what I'm looking for here is I want the function values. So I want those f of t values. So it's getting a little messy there, but I do want to have the bottom half highlighted for us there. So we're looking at 78 to 83 degrees. Now, yes, 80 has to be somehow in between 78 to 83. So this will be the interval I'm looking at. But remember, I want this interval to be in terms of our function. So if I scroll back up to kind of our template for this, we want to be looking at this f of something less than that magic number less than f of something else. So instead of writing down 78 and 83, I want to write down f of 90, because in this case f of 90 is equal to the 78, and then I want to write down f of 120 since that is equal to the 83. I'm going to my scratch work up above. I don't want it to get us confused with our kind of final thought process, but we have since f of t is continuous, and because f of 90 is less than our magic number of 80, is less than f of 120, then here comes our conclusion. So then, by the intermediate value theorem, there exists, there exists, in this case, a time. So let's get specific since this problem was dealing with time and temperature. So there exists a time, let's call it time t, in between the interval from 90 to 120. So remember, 90 and 120 is time 90 to time 120, such that f of that value t has to be equal to 80 degrees in this case. So we stated the conditions were met. So we stated that our function f of t is continuous because they actually gave that to us in the problem. We stated our interval, so specifically we narrowed it down as much as we could. So between f of 90 and f of 120, we would have to pass through 80 degrees. So then, by the intermediate value theorem, there exists, that's an E, I'm sorry, there exists a time t in between 90 to 120, since that's the time interval, such that f of t is equal to 80 degrees. So we can see, although it's different information that was given, since I'm not directly given a function, I can still interpret the information using the table and think about the scenario that is happening and then formulate our argument through meeting those three steps. Let's look at our last example. So example 4 here says, let h of x be a continuous function. Whoop, keyword. That should start to be jumping off the page at you right away once they start telling us that functions are continuous. So let h of x be a continuous function on the interval between -2 and 4, as shown in the table below. Then it asks us, what is the minimum number of times that h of x has to equal 0? Justify your answer. So this is a little bit different. It's not asking me exactly to prove that there exists a time. Instead, it's saying, what is the minimum number of times that h of x has to be equal to 0? So if I think about this on a graph, what I'm looking at is the number of times that I'm going to cross the x-axis. So on a graph, h of x would equal 0 anytime I cross the x-axis. So I'm looking for any places where I switch signs, where I go from a negative to a positive number, or where it flips and I go from a positive to a negative number. We're given a table of 7 pieces of data. So in our top column, I have the x values going from -2 all the way to 4. And then I have their corresponding y values, or their h of x values, as whatever they correspond to. So why don't you guys think about this? What is the minimum number of times that h of x would have to equal 0? So what we're looking for is how many times do I switch signs and go from a negative to a positive y value, or a positive to a negative y value. So let's look through this. I'm going to take it one step at a time. So if I look at the first two set of data points, from at x equals -2, I'm at -4.1. And then at -1, I'm at -2.5. So there's no sign change there. They're both negative values. Then at -1, I'm at -2.5. And then when x equals 0, I'm at 1.3. Well, right there, I have a sign change. And because of that, at some point, because my function's continuous, I have to somehow pass through 0. Then between my next 2 points, from 1.3 to 3.2, there's no sign change. But then at x equals 1, I'm at positive 3.2, and then at x equals 2, I go to a negative 1.3. So again, I have another sign change, which means that I have to cross through 0 somehow, at least once. And then on the rest of the points, I am at -1.3, -4.3, no sign change there. And then -4.3 to -5, I also don't have a sign change again. So a couple things to keep in mind. We're asking us now, what is the minimum number of times this is happening? Well, my minimum number of times would have to be 2, since based off of this table, there are 2 places where the y values switch from negative to positive or positive to negative. Now that is the minimum number of times. This could happen more than those 2 times, but it's guaranteed to happen at least twice. And that is what the problem is asking us to state. Now the way we justify this is still using that intermediate value theorem, since that's the theorem that guarantees that sign change. So let's start with the first part of our argument here. We need to state that f of x is continuous, or in this case, h of x is continuous. So let's start with that. Since h of x is continuous, and usually here we state that data that we're computing. Well, in this case, we're actually computed it twice, since we're showing that I have to pass through 0 between this -1 and 0 value and then the 1 and 2 value. So I'm going to need both of those intervals on there. So the first interval is h of -1 is less than, that magic number 0 is less than h of 0, since that's where I went from -2.5 to 1.3. Remember, that has to be equal to h of -1, since that was the x value, and 1.3 is equal to h of 0, since that's the corresponding y value. And we also have the second inequality. We have between 3.2 and -1.3. So in this case, since h of 1 is bigger than 0, since I went from the positive to the negative, which is bigger than that h of 2 value. And remember that 3.2 is that h of 1, it's an equal sign, and this -1.3 is that h of 2. In this case, I flipped the sign since I'm starting with the bigger to the smaller value. So we've stated that our function is continuous. We have our mathematical statements here of our inequalities. So then we can conclude this using our theorem. So then by the intermediate value theorem, so by IVT, there exists, in this case, at least 2 points, or 2 places, so I'm going to call them places instead, in between, there we go, in between -2 and 4, since that's the interval we're working on the x-axis. There exists at least 2 places in between -2 and 4 such that, sorry, we're having issues with the pen, so such that h of, in this case, oh, I didn't give it a name. So then by the intermediate value theorem, there exists at least 2 places in -2 to 4 such that h of, let's just use x, is going to be equal to 0. Since we were really asked what is the minimum number of times, we want to include that as part of our answer then, as we're justifying using that intermediate value theorem. So we can see in these last 2 examples, we don't have to necessarily be given a function like f of x equals this equation. Instead, we can be given data points and use those data points to interpret what is happening through either drawing a graph or thinking about as you're crossing those magic numbers. So in this last example, we were looking to see how many places my y value would be equal to 0. So to cross over 0, I'm looking to go from a negative y value to a positive y value, or a positive y value to a negative y value. Again, in this example, that's just the minimum number of times it could happen. It could happen more than 2 times, but all I am guaranteed is that it happens at least 2 times. So that's all that I can state in my justification then.